Hi everyone, my name is Hong Jin, and now I will present our work on test mimicry to assess the exploitability of library vulnerabilities. Modern software development involves the heavy use of third-party libraries, and it has been estimated that up to 80% of applications are now third-party code. This widens the attack surface for malicious attackers, and it is therefore important for software engineers to be aware of the risk of vulnerabilities in the libraries that they use. Vulnerabilities can be found in libraries. For example, if we were using a library to handle the unzipping of files, there's a particular type of a zip file that is known as a zip file queen. A zip file queen is based on the idea of a queen, which is a program that produces its own source code as an output. A zip file queen is a zip file that contains an exact copy of itself, and when unzipped, would produce a copy of itself over and over again. And zip file queens are also known as self-reproducing zip files. If a zip file library does not correctly handle a zip file queen, then it is vulnerable to a denial of service attack. And in turn, if we were to use a library containing such a vulnerability, we would also be susceptible to a denial of service attack if it is possible for our client program to pass a zip file queen to the library. And therefore, it is important for developers to be aware of such risks. And one way of doing so is the objective of our research, which is to produce a test case that executes a client program to confirm that a library vulnerability is exploitable. Prior approaches to warn developers of vulnerable dependencies may only do an analysis based on the dependencies, warning developers as long as a vulnerable library is found among the dependencies. But this may not be enough, because this may result in a large number of false alarms. And at up to 73% of projects do not use the vulnerable parts of the libraries. To improve on the state of things, some approaches would perform a reachability analysis based on a call graph. Developers would only be warned of the vulnerability if there exists a path from the client program to the vulnerable library function based on the call graph. However, the reachability of the vulnerable library function does not necessarily imply that the vulnerability is exploitable, because a static call graph analysis would not account for control flow, and even in a dynamic analysis, the vulnerabilities may require specific inputs to be triggered. And this motivates our approach, which is to generate test cases. However, we have to overcome the fundamental challenge of missing domain knowledge. A vulnerability may require very specific conditions to be triggered, such as hard-to-reach program states or inputs that are hard to generate by chance. For example, it seems unlikely that we would be able to generate a zip file queen purely by chance. And fundamentally, we lack a way to say how interesting is an input or a program state with respect to a vulnerability. But for a subset of library vulnerabilities, we would have more information from the library test cases, which is an overlooked source of information. Many times, vulnerabilities would be fixed with an accompanying test case, and this test case will give us more information about the vulnerability. Here we see an example of a test case that was modified when in the fix for a vulnerability in Apache HTTP Components client. In this test case, we can see the examples of an input that would trigger the vulnerability, as well as the relevant functions and the relevant objects that would need to be constructed to invoke the function. And therefore, this motivates our approach, which we term test mimicry, which aims to generate test cases for a client program based on the library test cases. Given a library test case, LT, which executes the library such that the vulnerability is triggered, we aim to generate a test case for the client program, CT. So we would construct CT based on LT, and CT would execute the client program such that it invokes the library in a way where the vulnerability is triggered. CT would be helpful because it would act as evidence that the client program can trigger the vulnerability. So to start off, we would first instrument the library code and then execute LT, the library test case, and we would target the same lines and branches that were covered in LT. So in other words, we try to guide the generation of CT to cover the same program locations that were covered by LT. But this is not enough because this does not address the problem of missing domain knowledge. What kind of input should we generate and when do we stop? To address this issue, we look at the literature of software testing and we find a very relevant technique known as test carving. Test carving addresses a related but different problem. That is the task of extracting unit test cases given a system test. Say we have a system comprising of 2 units. The system takes a URL as an input, and the first unit fetches the contents of the website associated with the URL, and then the second unit extracts a piece of information from the website, and this is the output of the system. If our focus was to generate test cases for unit B, then it would be very inefficient to try to run the system test over and over again, because the system test performs some expensive operations such as a network call to fetch the website associated with the URL, and doing this over and over again would be very inefficient. However, one challenge is that we need to replicate a valid program state for testing unit B. And to do so, test carving proposes to save the program execution and then to replay them up to the relevant program state associated with unit B. And by saving its execution and capturing the program state, we can then start the test cases at the point of the captured program state and focus on testing unit B. Test mimicry has many similarities and many goals that are aligned with test carving. We have a larger system here comprising of the client code and the library. We have a test case, LT, that executes the library code in such a way that the vulnerability is triggered. However, we wish to abstract away some parts of the library code, but we do so by capturing the program state associated with the triggering of the vulnerability. And our focus is then to generate test cases, CT, for the client program. And this is the focus, and what we try to do here is to generate test cases that execute the client program in a way that reproduces the same program state that was reached in the library code, or in other words, the program state that was associated with the vulnerability. So our task can be formulated as a search-based test generation task, and the search goals for this task can be constructed based on an extracted program state. So the goal is, of course, as earlier mentioned already, to reproduce the same program state associated with the vulnerability. So we can also view our task as a multi-objective search-based test generation task. While the goal is to recreate the program state that is associated with LT, we can consider that the program state consists of multiple aspects, and then each aspect would have one goal associated with the reproduction of that one aspect. We implement our framework test mimicry in a tool named transfer. Transfer aims for the reproduction of the same library behavior that was observed in the library test case. And to do so, we will instrument the vulnerable function VF to record the arguments that were passed to it in the execution of the library test case. So when we execute the library test case, and then we obtain the search goals based on the recorded arguments, and then we would design fitness functions that measure the similarity of a given generated client test case with the captured library behavior. So we will do this by comparing the program state that is reached by the client test case against the program state that is reached by the library test case. We will design fitness functions for the comparison of the different aspects of the program state. Essentially, we perform a direct comparison of the values that are captured in the program state. For string-like values, we will compute the edit distance. For primitive and enumeration values, we will directly compare their values. Objects are compared based on the externally observable state. Files are treated as objects. However, files read from the file system by LT are also made available to transfer. Exceptions are compared based on the types and exception messages. Apart from constructing the search goals, when we execute the library test case LT, We would also record the objects that were instantiated during the execution of LT. So these objects are added to an object pool, which is provided to the evolutionary test generator, which can then instantiate the same objects when trying to test the client program. So together, the object pool and the search goals that are obtained from the execution of LT are then provided to the test generator, which runs a standard evolutionary test generation pipeline. We start off with a randomly initialized population of test chromosomes. The test chromosomes are evaluated based on the fitness functions, and then the top test chromosomes are selected for further mutation and crossover to produce new test chromosomes. And this process repeats until the search budget is consumed or the search goals are satisfied. Transfer is built on the infrastructure of EvoSuite using the Dynamosa algorithm. In our experiments, we studied 22 vulnerabilities from 18 libraries. The vulnerabilities exhibit diverse behaviors, ranging from crash-like behaviors such as timeouts or out-of-memory errors, to incorrect functional behaviors such as network calls to an unexpected host. We studied 64 client programs using the 18 libraries. For 42 client programs, the vulnerability can be triggered. For the other 24 client programs, the vulnerability cannot be triggered. Transfer is compared against Siege, which was a previously proposed test generation approach, and we used a search budget of 10 minutes and executed our experiments on a standard laptop. Transfer outperforms Siege in detecting the library vulnerabilities by about 40%. And for the 24 cases where the vulnerabilities could not be triggered, we note that existing call graph approaches would produce false alarms because the vulnerable function would appear to be reachable based on the call graph. Our experiments focus on libraries ranging from a wide range of domains, from file compression to data encoding to web development. So this suggests that our approach is not limited to a particular domain, and it is likely to generalize. So why did transfer work? Here's an example of an extracted set of triggering conditions or the captured program state. And the key to triggering a vulnerability in this case, which this vulnerability is related to the earlier example we've shown about the vulnerability in Apache HTTP components client. So the symptom of the vulnerability is that the library would make an incorrect network call to an unexpected host. And this happens when a malformed URL is provided. So in this case, we see that the malformed URL is captured as part of the program state. And this allows transfer to guide the generation of a client test case that satisfies this triggering condition. And this fundamentally allowed transfer to generate complex inputs, which is the key to satisfying this set of triggering conditions. But at the same time, we note that there were irrelevant aspects of the program state that were captured, and this would throw transfer off. So as a next step, we would like to be able to identify the key conditions for triggering a vulnerability. Furthermore, right now the comparison of the program states are done directly based on a comparison of the values. However, in some cases, vulnerabilities would require more expressive conditions that transfer currently does not support. In summary, we have looked at the problem of mitigating false alarms with regards to vulnerable dependencies, and our approach aims to generate test cases to confirm the exploitability of library vulnerabilities. Our approach addresses the problem of missing domain knowledge by using the library test case, and the goal is to construct a client test case based on a library test case such that the client program will be executed to reach the same program state that was reached in the library test case. Our approach is implemented in a tool named Transfer, which is a search-based test generator. The search goals are extracted based on the program state that was reached in the library test case. So that's all from me. Thank you for your time.